I'm Adam Lane, I'm the team lead, and I'm an optical engineer.
Hi, I'm Carolina Caraya, and I'm an optical engineer.
Hi, I'm Jason Dilla, and I'm also an optical engineer.
Hi, my name is Alan Miller, and I'm an optical engineer.
Hi, I'm Justin Scott, and I'm also an optical engineer.
The main goal of the project was a proof of concept that a spectrometer featuring a Fabry Perot cell could be designed and constructed using widely available parts. The purpose of the spectrometer is for hyperspectral imaging and wavelength identification of sources from low orbit or LEO. Current methods of space-borne spectroscopy are expensive or involve too many parts that prevent usage outside of specific purposes. In general, this has applications in chemical identification in soil to aid in agricultural development or smoke in the air to aid in the detection of wildfires. Specifically, this type of spectrometer can be used for wavelength identification of artificial sources while filtering out background lighting. An example of this use is in LiDAR, where background solar light can be filtered versus light from stoplights.
Spectroscopy is the measurement of spectra produced by interactions of light with matter. A sample of light is broken into all of its constituent wavelengths, or colors, and the intensities of each present wavelength is measured, producing what is known as the spectrum of the light sample. A spectrometer is a device that can perform spectroscopy and typically uses a diffraction grating in order to achieve spectral decomposition. However, in our system, the spectroscopy tool will be the Fabry Perot cell, which is a novel use of this optical structure. A Fabry Perot cell is an optical cavity bound by two partially reflective surfaces. It generates interference patterns and will only transmit light at wavelengths that match its resonant wavelength. This resonance stems from wave interference. Light exhibits wave-particle duality, and the light waves will interfere with one another constructively or destructively based on the wavelength and phase of each wave. This phenomenon is currently used in noise-canceling headphones. In a Fabry Perot cell, the partially reflective surfaces will cause the incident light to reflect back on itself. If the wavelength is not close to a factor of the mirror spacing, the wave will destructively interfere with itself and be eliminated. The resonating wavelengths can be characterized by the cavity transmission equation, which describes the percentage of incident light that will be transmitted. Factors that influence this are the input wavelength, mirror reflectivity, mirror spacing, and orientation of the mirrors. We can use this equation to control which wavelengths will actually resonate and be transmitted. The Fabry Perot cell also filters out background lighting by an extension of this principle called coherence filtering. Most light sources emit a broad spectrum of wavelengths, not just one, with each wavelength traveling at a different speed in air. Because of this, the wavelengths will slowly separate as they travel. The wider the source emission spectrum, the shorter distance light can actually travel before the wavelengths separate, which is called a coherence length. We can adjust the cavity length with this coherence length in mind such that the cavity filters out broadband background light.
To understand how the Fabry Perot cell works and how various characteristics affect the transmission, we have modeled the cell in MATLAB. There are a few key factors that affect the system's performance, such as mirror reflectivity, actuator step size, total cavity length change, and camera frame rate. Using these factors, we can model the transmission as a function of cavity length for each wavelength across the visible spectrum, which we define from 400 to 700 nanometers. It then performs a Fourier transform on this data to observe the frequency at which the light will resonate. We found that mirrors with reflectivities of 90%, a cavity length of 5 mm with a total cavity change of 25 microns, and 25 nanometer steps per camera frame would provide sufficient data for the wavelength identification. This model was crucial for selecting proper mirrors, actuator, and detector to meet the system requirements. Our system must be able to create an image, so we designed an imaging optical system around the Fabry Perot cell. This must be done while meeting the system requirements of a 6-degree half field of view, a spectral resolution of 2.5 nanometers, and an angular resolution of 7.5 arc minutes. The main challenge when designing this optical system is the light rays entering the Fabry Perot cell must be near parallel, driven by the spectral resolution requirement. This means that the maximum ray angle that could enter the cavity would be 0.7071 millirad, or 0.04 degrees. To get the incident rays from 6 degrees, specified by the half field of view requirement, to 0.04 degrees, the lens system in front of the mirror would need to have a magnifying power of 0.0067. To circumvent this, we used the calibration approximation and said that we can increase this by 20x to 0.134 if we calibrated the system at 20 points. The lens system in front of the Fabry Perot cell would be a reverse Galilean telescope consisting of a negative lens followed by a positive lens placed so the resulting rays are afocal. The magnifying power is defined as the ratio of the focal lengths. We used a lens with a focal length of negative 10 mm for the front lens, followed by a lens with a focal length of positive 89 mm. Both are off-the-shelf achromats to ensure low cost, high availability while keeping the chromatic aberration to a minimum. The lens group after the cell is a 100mm focal length achromat airspace doublet, which allows for better aberration control. The required focal length was calculated from the detector height, half field of view, and Galilean telescope focal length. The spacings were all then optimized in Zmax at 550 nanometers, which is the center point of our spectrum, for both the RMS spot size and the Fabry Perot ray angle. The result was a system that was under a foot in length and meets the minimum half field of view requirement. The angular resolution was calculated using the RMS spot size of the 6-degree off-axis field at the most aberrated wavelength, which is 400 nanometers. The system was then toleranced using commercial tolerances for surface quality, element decenter, and tip and tilt. After the optical system was designed, the mounting system for the optics and detector was designed using off-the-shelf parts modeled in SolidWorks. This helped us determine the various mechanical parts we needed to purchase.
Based on our models, we determined that the mirror needed to be around 90% reflective and 10% transmissive. Traditional off-the-shelf options did not meet our specifications, and custom-made options were outside our cost and time budget. Plate beam splitters are a cost-effective solution that could meet our optical specifications in theory. Experimental results concluded that each mirror had about 7% transmission and 93% reflectivity, satisfying our allowable range based on our models. Off-the-shelf lenses were used to meet our resolution and field of view requirements. Here are the lenses we used. The major component is the piezoelectric translation stage actuator. It was selected via trade analysis, considering the cost, step size, and ease of mounting. The piezoelectric crystal within the actuator expands and contracts as the voltage is applied along 1 degree of freedom. Our actuator has a theoretical step size of 0.76 nanometers. The overall mechanical design is a 30mm gauge system. This helps keeps all elements centered along the optical axis. We had a problem mounting the 6.25mm lens as the lens was too small. The problem was that the mirror mount had too much friction with the rail, causing the actuator to tilt the mirror, disturbing the optical alignment even after adding lubrication. After weighing our options, we determined that drilling the mirror mount holes to reduce the tilt was the best option. A monochrome detector is used because the Fabry Perot cell determines the wavelength incident on the detector. The detector was based on the cost and its software capabilities. There are two software components: the interface software and the image processing software. Interface software essentially combines the software for the actuator and camera to run simultaneously to generate the frame data. The image processing software identifies the wavelength and generates our images by corresponding each frame with the cavity length.
Here's our constructed system with the detector removed in order to visually see the fluctuation in the focus laser spot. The intensity changes as the actuator moves, illustrating how the transmission through the Fabry Perot cell changes with the cavity length. We can also see how different colors resonate as the red and green laser resonate at different points as the cavity length increases. Here the image plane is placed beyond the focus to observe the fringe patterns, which is done to better visualize the resonation points for each color. At the end you can see the fringes changing in lines, which indicates the tilt due to friction between the mirror mount and rails that was discussed earlier. In summary, we have gone through an adaptive design process to create the system that meets the project's primary goal as a proof of concept of the Fabry Perot spectrometer. We hope you enjoyed the video and came away with an understanding of our project goals and design. Thank you.